then I'll take it away and I'll introduce a guest. Hello, everyone. May I have your attention, please? So today we have a speaker who's, Associate Professor Makro Kanedi from the King Abdullah University of Science and Technology, our neighbors over in Saudi Arabia. And I'd like to say, a few words about speaker before we begin. So apologies as I'm going to read off your website bio. Professor Kanedi, his research interests are the principal construction and operation of large-scale network computer systems, specifically in distributed systems, large-scale computing, and computer networking with emphasis on cloud programming and programmable networks. So this is with applications to machine learning and also other applications outside the realm of machine learning, right? So his current work focuses on improving network systems design, implementation, and operation along several vital properties such as reliability, performance, security, and energy efficiency. And I'm sure we all got the memo that sustainability is going to be a big topic in the UAE this year. So it is with a lot of excitement that we have an expert here on the hardware side, especially to complement all the software work we do in and around machine learning. So with that,
all right.
Marco, could you begin?
Thank you so much, Sharon. So press the button. Do I have to stay here?
No,
the mic?
You can walk around.
Okay, the mic will pick. So I've been given the clicker, so that's a lot of fun. And that also reminds me that I should be updating my website because I thought I crafted a better bio for the talk. And I even asked ChatGPT if it could tell me what the next big thing should be. Disappointingly though. All right, so it's a great pleasure to have received this invitation. Of course, we are in the University of AI, and so I thought I will basically talk about programmable networks for distributed deep learning. And this talk is going to be about a lot of the advances and some of the perspectives that I have in this field. But let me start, by saying, obviously to you, this means a lot. There's probably no better time to be alive, right? Because we are witnessing the era of the big models. Now we can generate images. We can ask an AI to tell us how we're going to get our living room refurbished if we want to, or we can entertain some dialogues with ChatGPT and have it explain to us bubble sort in the style of a gangster movie, and so on and so forth. But really what I like to stress is that this era has been enabled by this virtuous cycle that I really like to describe in that people like some of yourself creating the latest breakthrough in AI are doing so by creating ever sophisticated models thanks to more and more data that is being collected and become available. But underneath it all, really the innovation that is happening because of the leaps in infrastructure that is enabling all of this to grow. I'm referring to the clusters of hundreds of machines, each with many hardware accelerators like GPUs, CPUs, and so on. And in spite of that, you're never satisfied, right? So the compute requirements are already mind-boggling, and they are always growing up, right? Maybe doubling 3 months, I think it's probably an old quote from OpenAI, and now it's even more. And so as a consequence of that, it takes a long time to train some of the models, maybe days or weeks, and it takes a lot of money and in turn energy as well. So that is all clear, but I also want to paint a broader picture about what deep learning workloads look like to a person like me. So I am, as Sharon introduced me, my background is in computer networks and distributed systems. So I'm a systems researcher at core, and I work on systems support for AI. And so when we talk about machine learning training, right, you are primarily thinking about the algorithm and perhaps delegating it to some PyTorch or TensorFlow of choice for your training framework. But in reality, as a systems person, I like to think of it as the whole holistic and full picture. And so this slide portrays, really what needs to happen if you're training models in production. You are not just focusing on the GPUs and the training cluster and the interconnect of that. You're also thinking about the storage that will host that data, how that data may need to be encrypted, and what the requirement for that accessing data will be like. And then in the middle, you're going to think about the distributed pre-processing, because there's always kind of an impedance mismatch between how the data you have collected is available and what you really need to do in order to feed it into the GPUs to train models. And of course, deep learning today is primarily a compute-intensive workload. It makes, after all, usage of all of these GPUs and TPUs that I was telling you about. But we really need to be mindful of the scale and the trends involved, especially as the number of data transfer that are involved increase. And that is essentially how I connect programmable networks with distributed deep learning. So in this talk, I'm going to focus on these two segments of the workloads, the training cluster, and then later I'll come back and talk about the pre-processing transformations that need to occur. But let me first review some of the trends in deep learning from algorithmic and technological perspective. So one thing that obviously has been established is the more data, the more parameters, the more compute you can do, right, leads empirically to better model quality, and that has been witnessed with exponential growth over the past years in terms of how much compute, for example, we can throw at first it was about the CNN networks primarily, and more recently about the transformer architecture that have much higher scaling in demand. So particularly thanks, if you will, to their self-supervising nature in terms of training and less requirements for data, labeled data to be available. In comparison, what you can see here, it's also an exponential curve. The black line is Moore's law, right? So it's 2x doubling of transistors every 2 years, which is really lagging behind in terms of the compute requirements for the largest models. On the right-hand side, though, you see another thing that is happening, which is a very important trend known as the memory war for AI. And the trend here portrays the demand for memory as essentially we train the models. And in the green line, you can see how memory is actually scaling across GPUs or TPUs, right? So that exponential is a much slower one. And that means that deep learning is not just a popular trend and workload, it's actually a distributed workload necessarily for the foreseeable future. And therefore, we must exploit parallelism in many of its forms, starting from perhaps what the most straightforward is, which is data parallelism, and it will be the focus of most of my talk, as well as the more advanced pipeline or model parallelism, and more recent intratensor parallelism strategies to accelerate and make it possible to even train some of the models at scale. So having these trends in mind, let me contrast with what is happening if I compare GPU trends versus network trends. And when I use the word network in this talk, oftentimes I would actually be referring to computer networks. I apologize if that creates any ambiguity. So on the left-hand side is what NVIDIA reports to be over the stretch of 6 years and 4 generations of GPUs, the performance increase that they have been able to achieve, not only thanks to Moore's law, which would set you at just an 8x, but thanks to cross-layer performance optimizations of co-optimizing software and hardware. And so they say it's, for them, 26x performance improvement in 6 years. On the right-hand side is the latest, the LoRa Group Data Center Ethernet report that informs us in terms of the deployment of Ethernet technology. This is converged Ethernet is essentially where all of the network in the data center is heading to, despite the availability of InfiniBand that you might be familiar with if you use training clusters. More and more so, it's becoming Ethernet. And this plot here informs in terms of volume in millions of deployed switch ports in the data centers. And the bars are being colored across different technology, different network speeds, starting from 100 gigabit per second all the way to 800 gigabit per second. The main takeaway, without really studying the plot, is that these measurements and these are projections. You can see how slowly newer networking technology is actually replacing the current predominant one, which is 100 gigabit per second. And so I would like to essentially emphasize that and raise the awareness that networking is not scaling as fast as compute. On the other hand, right, what we are observing is that the larger DNN models, which are also the bigger one, and these plots are going to be towards the right, are the ones that spend more and more time on communication. And so because the compute accelerator performance improvements have outpaced network bandwidth increases, we find ourselves in the situation where a lot of the percentage of time that we are spending on every iteration of our SGD or ADAM or whatnot while training the neural network is actually being spent on communication, which represents a severe bottleneck to training efficiency. And here we had experiment at both 10 and 100 gigabit to just see whether a 10x improvement in networking speed would potentially solve things. And of course it does better. So you can see that the percentage spent in iteration time in communication is lower. But for large models like recommendation models, BERT and DeepLight, there is still a very significant amount of time being spent in communication. And some of that communication is not being overlapped with computation, which also is a problem. So where does that communication come from? So I mentioned I'll primarily focus on the data parallelism part of distributed DNN training. And I'd like to review with you what is happening. When you think about PyTorch and TensorFlow, you think about your optimizer.step. But really, if you're running in a distributed mode, what is happening when you invoke that optimizer.step? Well, essentially, it's the gradient synchronization part of the optimizer, where hundreds, if not gigabytes of, hundreds of megabytes, if not gigabytes of gradient data essentially has to be communicated in an all-to-all pattern, because every machine holds a copy of the model and every machine has partial gradients. And now we need to find the average of those gradients. And this is a very intensive communication for the network. The machine learning community recognized this and early on proposed the parameter server architecture, which was a bit of a stopgap measure in the sense that it became clear that having a centralized, dedicated set of resources could indeed help, but it could also become a bottleneck. And later on, a different architecture known as O-reduce became more popular. This is what typically gets used today, also thanks to the specific implementation primarily done by NVIDIA with their Nickel library that have really optimized collective communication for GPUs. And the idea in the O-reduce is to form some kind of logical topology, typically a ring or a tree, and then exchange the gradient data over that logical topology in some sorts of peer-to-peer communication, pairwise communication between GPUs until you have synchronized all the gradients. Beyond this, if we go one level deeper, there is this story about compute and communication overlap that I briefly mentioned before. And that is, if we actually analyze what's happening in data parallel training of a neural network, as we essentially go through the forward layer and then, the forward pass of all the layer, computational, the loss function, and then back. As we start to go back, right, gradients become partially available with each layer of my neural network on the backward pass, and then I need to synchronize. So every one of these red arrows that you see here relates to the gradient synchronization for a particular layer of my neural network. And if I zoom in into one of the workers, really what is happening is as we compute partially in the backward pass, these gradients become available. And the overlap that we can start to introduce is that as soon as some of the gradients are available, then perhaps this has got battery issues. So as we start to compute, then immediately we can overlap some of the communication to the ongoing computation of the subsequent backward pass layers. And so what I want to stress here is that obviously in certain, depending on the model architecture, you may be in a situation where you really can only wait on the network to complete the gradient synchronization before you can start the next iteration. And so there is ever so much that you can do in terms of communication and compute overlap, and that is going to represent a bottleneck. So when I refer to it as this network communication bottleneck, really you can think in the first order as the ratio between communication and computation done in a particular model being important, but on a second order approximation, it really pertains to the non-overlappable amount of communication. And here is a real measurement from the deep flight recommendation model, where you can really see on a V100 GPU, the amount of communication that is happening over the network is substantially longer than the time it takes to compute the entire forward and backward paths. All right, so what's our main suggestion here? So we have introduced a concept we call in-network aggregation, where from an infrastructural perspective, coming at this problem, we were simply driven by this question of seeing all the data being exchanged either over a parameter server or in a peer-to-peer fashion over a logical topology. Is there something instead that the infrastructure could do? And it turns out that we can leverage certain technological trends that seek to create deeply programmable data planes in essentially commodity Ethernet switches that you would deploy in data center environments. I'm going to pick particularly as an example the first platform that really introduced this concept and made it possible, although I would note that many other vendors to this day have introduced similar offerings. And so the one I'm going to talk about is the Barefoot Tofino switch chip, which when it first was announced, the first version was 6.5 terabits per second at 100 gigabit line rate processing for each port on the switch. And this was a picture, Chaos was actually fortunate in that as a university, we were probably the first university to ever acquire this platform or toy, if you will. And Barefoot was later acquired by Intel. So today we really should call it the Intel Tofino chip. And what is this technology? So essentially, instead of giving you a prescribed ASIC that understands all the network protocols that you might have seen in a networking course, if you go back to your undergrad education with maybe Ethernet, spanning tree, IPv4, IPv6, and so on, this is a blank slate when it comes to knowledge of network protocols. It contains a parser and a deparser to arbitrarily parse information that is packetized into the network datagrams, and then it has resources in the form of match table and action macros stages. And these are all replicated so that you have many more resources to create arbitrary packet processing pipeline. So you have to imagine that then it becomes possible to use some programming language, which in this case is known as the P4 programming language, to create a parser that decides exactly what information you want to extract from a packet. And then you can fill precisely logic in these matched action tables that determine how you would process fields from the packet or information that lies in the packet. And then you can create control flow graphs that decides, on the basis of that information, what kind of logic to apply and what kind of match actions to apply to any particular packets. So this technology essentially made it possible for us to create the first co-design of distributed machine learning and the networking substrate that it really needs to be able to accelerate data parallel training. We have to deal with several challenges, however, in creating this design. And those arise from the particular characteristics of this type of hardware that I mentioned. Limited amount of computation that can be performed for every packet, as well as limited storage. You can think about storing hundreds of kilobytes of data inside that switch chip because it's very fast memory, but you cannot essentially replace a parameter server with such a chip. And then there's no floating points, which is the backbone for distributed SGD. And since we're talking about a network design, we have to deal with the inevitable possibility of packet losses. So our design came up with an approach that we call a pool-based streaming aggregation protocol that makes it possible to aggregate gradient data without having to store all of that data inside a network. And then we leverage the ability of fine-grained computation at the host side combined with what the switch can do in order to deal with the other limitations, such as the lack of floating points that forces us to do quantization at the host, or failure recovery that works by having timeouts carefully tuned in order to recover from packet losses. And last but not least, we are really targeting the fastest possible performance that we can achieve, and therefore that requires using RDMA on the host side. And that led us to create our own in-switch RDMA implementation to be able to speak the same protocol supported by the hosts. So I will not really have the time to enter the details of all the design, but I want to give you some good flavors in terms of how we architected the system. So from the start, let me talk about the streaming aggregation protocol. So what you see here is a toyish example, but for this presentation, it will serve its purpose. You have different workers with different gradient data that is shaded with different colors. And at the bottom, you have this switch. And the switch, we view it in terms of abstraction as a pool of aggregation slot. An aggregation slot is something where you can aggregate several values from the gradient data. We call them chunks. And so we chunk the gradient data, and each gradient data could be, for example, 256 values, 256 gradients. And the workers utilize a streaming protocol where a deterministic mapping it associates the different chunks to different slots at the switch. And every worker follows the same deterministic logic. Now the switch knows the size of the machine learning job, so it can essentially count when a particular slot has been fully aggregated, and it can send back and broadcast the aggregated data to the workers. And that packet serves as an implicit flow control signal to the worker that now a slot has become empty and it's available for reuse. And therefore the workers can proceed by sending the next logical corresponding chunk to that slot. And this operation is essentially streaming in that we can keep on sending all the data, streaming all the data until we are done with our aggregation job. And what is really elegant about this design is also the fact that every worker can fully exploit the line rate at which it is connected to the switch, therefore leveraging 100 gigabit per second aggregation capacity. And we're not concerned of the fact that we are tightly coupling essentially to flow control across workers. The reason is that we exploit this property for data parallel deep learning, which is at the end of the day, gradient synchronization is a barrier. And so it's not going to move faster than the slowest of the workers. But at the same time, typically the GPUs have very high performance predictability. And therefore, it's fine to have this tight coupling.
So a quick technical question.
Absolutely.
When you say it's streaming, is there any, let's say, non-serializable semantics in the update, or it's still fully serializable, still respects iteration boundaries, etc.?
It's fully serializable.
Got it. So the streaming is basically background work that happens within the scope of iteration, but all of the updates have to be done before the iteration boundary.
Yeah. Thanks for the question. Okay, so as I was mentioning, the second ingredient to making this work is this combined switch host architecture, in which essentially we use the switch for what it can do best, which is fixed point integer aggregation, and we delegate quantization and failure recovery logic to the hosts. So I just mentioned this thing about quantization, so let me address how we do that. So the idea is that we have a chunk or a block of the gradients, and we want to convert between floating point values to 32-bit fixed point values. But of course, that could lead to a very high quantization error. So we want to limit the quantization error. And so here we are also a bit clever with the design, in that by leveraging the fact that the gradients were grouped into blocks, we can adopt a scaling factor that essentially maximizes the dynamic range representation of scaling from 32-bit floating points, let's say, to a 32-bit integer. And we determine a per block scaling factor that is optimized in order to minimize the quantization error. And in order to have something that does not hold us back, we essentially run the scaling factor computation as a one-step ahead computation with regard to the corresponding block for which it will be used in the future. That is, before we actually send that block, the ith block, right, at the I-1 block, we are basically sharing across all the workers the maximum possible scaling factor for the gradient values of the block, and then we actually scale it later. Yes.
So apologies for 2 interruptions in a row, but I don't believe you've explained yet the reason why we want to, like, what's the advantage of using fixed point computation over floating point? Did you explain that?
We're doing integer. Sorry, what is the question?
Right, because I'm not sure if our ML audience here is familiar with the difference between fixed point and floating point computation. So I thought it might be a good time to say a few explanations about it.
Okay, sure. I can take that. So typically, the way in which we can do representation of numbers can be an integer. So it's a fixed point representation, and so that gives you the best possible arithmetic performance thanks to just a simple ALU. But in machine learning, we need floating points, and in that regard, there's a few types of representation. There's the IEEE representation, FP32 or FP16, and then specific to machine learning, due to its compute intensity, there's things like pfloat16 and TF16, TF8 these days inside NVIDIA that use a different representation in which you have different bits in your 32 bits to represent sine, mantissa, exponent, and mantissa that give you different properties. Now, the issue that we have specifically is that the switch cannot work with this kind of representation, the floating point representation, and it would essentially. I'm going to touch on that a little bit later. So how one might go about implementing it, but the bottom line is if all you have is essentially an ALU and you can only do these integer additions, you have to convert the data representation, and that's what we actually do. And we exploit the fact that by having a scaling factor per block, we can really minimize the error of that scaling, because we can essentially recover, thanks to that multiplication and that division by that scaling factor, enough precision of those data that we're sending over the network. And to basically convince you of that, we have several results here. I'm picking just one ResNet model in which we were able to obtain the same test accuracy on a ResNet network using our system called SwitchML as compared to the baseline, which is one in which you do vanilla distributed training without any sort of quantization.
And here, because I noticed you use the word fixed point rather than integer, and to me, fixed point may include non-integer numbers that have a decimal point with a certain number of significant figures.
Okay, sorry, no. Then in that case, it's just integers.
Okay, so I should understand fixed point is simply integer in this case.
Yes, absolutely. Yes. Okay, so let me address now a relevant question, which is, how much faster is this system, SwitchML? And in order to find out, we created an implementation using before and a complex testbed that we set up in our lab in KAUST. And we measured across a host of different benchmarks and models how much faster SwitchML would be as compared to the NVIDIA nickel library using RDMA. And here I'm portraying two different results. One is in our network with just 100 gigabit per second, where we run the complete system, and the speed up is computed as the ratio of SwitchML over the nickel performance, where of course higher is faster. And this result shows that for different models, that type of speed up varies in proportion, as we said, roughly in proportion to the computation over communication ratio of the different models, and it reaches up to 2.27x performance improvements. Also, theoretically, we can also demonstrate that this kind of aggregation has a 2x factor improvement over doing nickel ring overuse in this case. And as a kind of toy experiment, because we had P100 GPUs that are now 4 generations old, those P100 are essentially too old for really having 100 gigabit per second network, if you consider a realistic cluster. So we tinkered a little bit with that and trade what would happen if we had 10x faster GPUs And so those experiments revealed that indeed, for the majority of the models, we will recover close to a factor of 2x speed up as opposed to nickel RDMA. Now, obviously, this is a good advantage, and it's an important one. But there is also a second property that makes SwitchML desirable, which is that its performance does not depend on the number of workers. Those results were obtained with eight workers. And we studied here, as we scale the number of workers from 4 to 8 to 16, and we compared the throughput, that is how many gradient elements per second we can aggregate with SwitchML in blue as compared to nickel in orange. How, not just how much better we are, but whether we can maintain as close to the max RDMA goodput on that network as we scale the number of workers. And that is indeed true for SwitchML, because as I said, by design, we can exploit the full line rate for each worker. Whereas in the presence of a ring overuse algorithm, you suffer as the ring size becomes larger. There's a latency component that also is introduced, and then it takes more time, and therefore it scales more poorly.
And could I presume that this observation holds up to the maximum number of ports?
And that is precisely correct. Yes. And so that is why our ongoing project is actually scaling SwitchML to be beyond the size of one single switch, but actually making use of multiple switches. Yes. Right. So let me go back to the discussion we were having on floating points and integers. And it was somewhat undesirable that we couldn't perform directly natively with floating point operations on programmable switches, such as the Tofino one. So we actually took a close look at the problem. And indeed, it turns out that today you will not be able to implement not even an approximate native floating point operation in the switches, but with a few tweaks to the PISA architecture, which is the underlying architecture of the Tofino chip, we demonstrated that it will be possible to implement really close to native floating point support without having an NPU, which would be costly hardware to introduce into these switch chips. And the result is also that by doing so, we can free up a lot of the CPU cores that are otherwise used in SwitchML in order to do the quantization, and therefore we can recover very good performance even with a minimum use of cores to do just the network I/O in that case. So let me recap. We introduced in-network aggregation, in which SwitchML performs data aggregation along the network paths using a best-in-class programmable network devices. And we demonstrated several benefits of delegating aggregation to the switches for distributed deep learning, including improving the training throughput, performing aggregation at the sub-RTT latency, that is sub-round-trip time latency, and one that is independent of the number of workers. And as an additional benefit, we can actually reduce the traffic on the network fabric, which means that available capacity could be used by other applications. So we created that SwitchML with essentially dense data in mind, but then we took a look at the actual composition of those gradients data that are being exchanged over collective communication. And we noticed that for several of the models, the data tends to be highly sparse, with particularly recommendation models having a lot of sparsity in the gradients. And therefore, we were wondering, can we efficiently aggregate sparse gradients and avoid sending a lot of zeros essentially over the network? So we extended our SwitchML protocol to create OmniReduce, which is a sparse streaming aggregation protocol, where the idea is very similar. So I'll go quite quickly. But we introduced a little bit of metadata that is associated with every block of the gradient data, so that we enable a centralized aggregator to keep track of what is the next logical non-zero block that should be streamed over the network. And we have essentially that logic to request that every worker only sends their non-zero blocks. And then this is what I'm showing this animation is one thread of computation. And of course, we parallelize this in order to saturate all of the available bandwidth through fine-grained parallelization and pipelining. When we created this protocol, OmniReduce, we were not quite sure we could have this additional complexity on programmable switches. Therefore, we did all of the project essentially as a software implementation at first, and only later, after we had conceived the entire protocol, we went back and demonstrated that yes, it is also possible to create this as an in-network aggregation with a slightly different flavor of the protocol from the one that I've shown here. But for the purpose of this result, we essentially implemented everything in software with RDMA and with floating points, and we compared against a corresponding version of SwitchML also built in software for fairness. And so here, I'm portraying the further speed up that OmniReduce can gain on top of SwitchML star, the one implemented in software that represents the one on the y-axis. And OmniReduce can achieve a further 2.23 times speed up for deep light that was very highly sparse, and then maybe a 40 to 50% improvement for some of the other models, and a lower improvement certainly for BERT is actually comparable. We also compare, in orange, you can see something called AG sparse. That is what PyTorch gives you by default. It's an ORGATher based sparse or reduced methods that we just perform as a comparison. You can see that this is totally something that you would not want to run. It's even in terms of performance inferior to SwitchML. And the side benefit of having done this project entirely in software first is that the company Meituan from China found a paper, and they first found a SwitchML paper, and then they told us, well, we're not going to deploy programmable switches, but since we have this thing in software, can we run this? And so then the answer was yes, you can run it, and they actually adopted it and ran it in the.
For CTR applications, is that?
That is for CTR, yeah, for recommendation models. Yeah.
One quick question here. So this just reminded me that now the switches, the programmable switches, have of course limited memory. So I wonder, right? Have you run into situations where perhaps some of the layer structure of larger models presents a memory management challenge for the aggregation? Like, how do you manage the fact that there's limited memory on the switch?
So at this very time is essentially just the streaming nature of the protocol that takes care of the problem, because it kicks in as a flow control approach. And so for as long as there is no space, then there is no data sent to the switch. And otherwise, by design, it means that there is some space, and so you can stream.
So that means from the worker's perspective, if they get ahead of themselves and need to work on set updates for part of the parameters that the switch is not working on actively, they're going to block.
Yes,
right?
it's
until
blocking.
the switch is done with its aggregation.
Precisely, it is blocking. We are investigating other forms of this, but for the purpose of what I discussed today, it's basically blocking.
Right. And then my extension to that question is that it seems that the blocking is not an issue for models in the less than 10 gigabyte parameter range. Do you have any forecasts or predictions of what might happen when we start going to the tens of millions of parameters or higher, right? Do you foresee any memory management challenges on the switch, or you think it's going to play out the same way that there's blocking, but it's going to be fine because it's fast enough?
It's a good question. I don't have a ready answer to that. My sense is that you need to, at that point, reason precisely about the communication patterns. If the communication pattern is something like a reduction, then I still believe that something like OmniReduce and SwitchML is a very apt solution, because it has certain guarantees in terms of consistency of that reduction, and it provides the ability to do the reduction in the network, which therefore removes some of the cycles from the GPU that would otherwise be occupied by the reduction.
Basically, we're exploiting the fact it's a sequential access pattern.
Yeah. However, this does not apply directly instead to the case of the more point-to-point communication, which may arise, for example, in your cross-mesh sharding work, as well as in applications of pipeline parallelism or intertensor parallelism. And in those contexts, the communication would tend to be, as I said, point to point. Omni-reduce would not necessarily help in terms of the in-network aggregation part, but omni-reduce happens to sort of be a generalization over the collective communication, and it can encompass not just reduce, but also broadcast and gather naturally due to the fact that the data is allowed to be sparse and not overlap spatially. And so going forward, we're very much invested in pushing for omni-reduce in the application of other larger models and ones with different style of parallelism.
Right, which is to say, instead of the data parallel style, there is some partitioning of the model, and therefore some point-to-point communication becomes unavoidable between the workers.
Yes. Okay. So I was recall that the last thing I was saying is essentially we built this in software. We had some success with Meituan, and the reason they didn't want SwitchML was they were unhappy with having to deploy a different generation. Different types of switches. So that actually made us think, well, there is a different type of programmable device that is emerging in computer systems that is called the SmartNIC, or nowadays it's called the DPU, the data path unit. And that started basically, that brought us to think, could we realize in-network aggregation in an entirely different way, that is using the SmartNIC to offload the aggregation. And that also has several implications and benefits for omni-reduce as implemented in software, in that omni-reduce in software requires these extra machines to do the aggregation, and it ends up having a high CPU utilization for I/O due to the fact that it has to reason precisely about the next non-zero block. So there's potentially benefits to using the SmartNIC as a dedicated hardware. We can save CPU cores, we can improve the scalability, and as I said, we do not have to have extra servers. So tempted by that idea, we actually ported the core omni-reduce software to the best in-class SmartNIC that you can get today, which is the Bluefield 2 from NVIDIA. It supports 8 ARM cores, 16 GB of RAM, making memory pressure far less of a problem in this context. And in our specific model, it has 2 ports by 100 gigabit each. So on the engineering side, we had to make some tweaks in terms of the threading model and the memory allocations of our software implementation. And then we ran some experiments, and we were testing what happens if we compare with our original omni-reduce aggregation that runs on an x86 server in blue, and the Bluefield 2 performance across 2 different levels of sparsity. Sparsity 0% essentially means dense data, sparsity 96% being a very generous amount of sparsity for the data. And this plot portrays latency, so lower is better. And what stands out is that, of course, here in this case, the x86 server has far higher performance, despite the fact that this particular x86 server is actually a 7-year-old server. So we essentially stumbled on some of the limitations of how omni-reduce fails to exploit the hardware, and how it comes to grasp with a low memory bandwidth over the DPU, as well as some potentially not scalable control logic, in that it's an O(n) square control logic where n is the number of workers for omni-reduce. So we're now pursuing different algorithm designs, and it's our hope to really be able to customize omni-reduce and run on SmartNICs. And this is very much ongoing work that we have. Now, connected to this, but also essentially switching gears a little bit, there is this other field of gradient compression, right, which comes at it essentially trying to achieve the same goal. Let's accelerate distributed deep learning. But the motto there is, let me reduce the data volume by performing lossy compression of the gradients, perhaps by quantization or sparsification or low rank decomposition. And once I have compressed the gradients, then I have less amount of data, and then I can send over the network and communicate it faster. And this is a very interesting set of proposals, in which interesting trade-offs between accuracy, training throughput, and also system level aspects like compression efficiency get actually introduced and exposed. And that is, from a mathematical perspective, there is certain implications to this lossy compression. And, thanks to, brilliant people like Sam in the room here and Martin somewhere on campus, we have beautiful proofs of theoretical convergence guarantees. And, in the ideal case, you have this thing that is the recovery of the asymptotic rate as with SGD, which, paper looks very good, right? But then when it comes to, really implementing a system, right, you really must ask this question: what's the issue? What's the implication of lossy compression? Because with smaller data volume, you can do clearly faster communication, and therefore you can, have faster iteration time. But due to lossy compression, you have statistical variance, and statistical variance may lead to more iterations for convergence. And so you really end up having a real speed up in a workload if this equation holds. That is, in your compression-based system, T times I is less than T times I in your original system without any compression. And we wanted to, really find out across the board for many of the different proposals in the space, what happens if you implement compression and you, try to run it and compare it fairly across, in our case, it was 7 different benchmarks. Here, there's one that exemplifies our results. And we portray both the measurement of the relative throughput, where relative is on the baseline of no compression, as well as the average data volume per iteration that is being exchanged, that is also on the y point on the x-axis. And the x-axis, sorry. The y-axis in this case is the accuracy metric of best hit rate. Higher is better. Now, I don't want you to really study all this plot. It will take us forever, but there's few key takeaways from here. So first, we basically observed that compression is not always a win. That is, in any data point that you see that is lower than 1 on the x-axis of the relative throughput, it means that by applying compression, you are effectively slower than if you had not compressed your gradients. And secondly, we observed that the volume and the quality not always correlate. In general, it is true that the more volume of data you send, the higher is the quality, but that is not applicable in general. And as you might have suspected, what we really take away from all this is that there is no one-size-fits-all compression that would equally apply everywhere. And that really demands that compression be done in a very workload-aware fashion, as well as in a systems-aware fashion with several types of optimizations that will make this a practical strategy to really accelerate the distributed deep learning. And so towards that objective, we have done several pieces of work. The first one, right, I'm actually proud that we did it with Sam when he was a student at KAUST, and we had devised this natural compression strategy that was about creating a quantization scheme that would round every gradient value to stochastically to the closest power 2. And then, we were having this discussion about floating point representation. Well, it turns out that once you round to the power 2, then you can basically take the exponent part of that floating point representation and only send that piece of information along with the sign, and then you can aggregate it using in-network aggregation. And then we have also done some more work in which we looked at possibly what is the lowest overhead type of compression, which is threshold-based sparsification, since it has a theoretical O(n) overhead, and you can clearly parallelize that massively through using a GPU. But the issue there was, how do you estimate which threshold to use for sparsification? So we had some theoretical contributions in terms of multi-stage estimation and making use of sparsity-inducing distribution that led us to, in the best case, a gain of 41x speed up in terms of time to accuracy for one of the benchmarks. And then we also consider what happens if you apply sparsification in the cloud, where essentially you may not be subjected by essentially fixed bandwidth across all the different nodes. You actually live in a dynamic network with bandwidth variations over time, and therefore fixed compression is an effective strategy. And so we came up with the delay-aware adaptive compression strategies that would couple compression with the available bandwidth, where the idea is you don't really need to compress if you have a lot of bandwidth, but as the bandwidth available shrinks, then you start to compress more. And even in that case, we were positive in finding successful speedups, meaningful speedups, as compared to a no compression baseline. In this case, the best case was a 5.3x with a top K compressor. So let me recap. We talked a lot about this network bottleneck in training, and I presented 3 different strategies and solutions that have clear interrelations. In network aggregation, where I presented switch amount to optimize the communication infrastructure and support aggregation. For sparse collective communication, we extended switch amount into omni-reduce and created the first efficient stream aggregation, similar inspired by in-network aggregation with sparse data. And then I presented gradient compression, work on gradient compression, where the idea is to reduce the data volume by lossy compression, and we'll be particularly careful in thinking at the problem from a systems perspective, and particularly exploiting this observation that generally this last approach involves a trade-off between the training throughput and accuracy. And actually, having done the work, and I don't have time to cover it today, but we actually applied gradient compression with omni-reduce, creating a version in which block-based sparsification in omni-reduce introduces more sparsity so that we could recover better performance, for example, in the case of BERT, that was not really satisfactory. Now, there is little time, but I've little left in my talk. So I'd like to go back to this slide and remind you that in the production setting, when we talk about the deep learning workloads, right, we have to basically be careful as to what happens in the pre-processing step for the training data. And what is really prompting us to take a closer look at this is a recent paper from Facebook, published in NISCA 2022, in which 2 key results can be stated as follows. So on the left, you can see for 3 different production recommendation models that they trained in Meta, the percent of total power that is distributed in storage, pre-processing, and training, where clearly you can see that at least in one case, the amount of energy that goes in pre-processing is higher than the amount of energy used for training, right? Who would have thought? The second key result on the right is a plot that is normalized, of course, because Facebook is not going to give us the real data, but still, it's the trend over the past 2 years for the dataset storage size growing by 2x over 2 years, and the online ingestion bandwidth. This is essentially the bandwidth used for the ingestion into the training cluster, which instead has grown by 4x over the past 2 years. And so if you basically put this together also in the context of the trend for bandwidth in the data center, this actually should alarm you in terms of the ability to further scale deep learning in production. And so we took interest in this project, in this problem. And so the pre-processing stage essentially is this transformations that need to be applied with, let's say, every sample or every block of your training data. And GPUs are arguably the most expensive part of your training cluster, so you certainly don't want to run them idle. And in order to avoid this data stores in which GPUs will be idle, you need to ensure that the pre-processing rate is greater than the ingestion rate. So how does Meta solve this problem? Well, they essentially have a disaggregated pre-processing layer in which they report they might use as much as between 9 to 55 CPUs for every GPU worker, which is overall very expensive and not energy efficient. But our observation is that based on what they told us in the paper and common practice, it turns out that a lot of the transformations that are applied to this training data are simple operations. So we asked, can we use in-network computing, right, to be able to absorb some of these transformations? And so leveraging our strengths in using Tofino switch, of course, we first approached the problem by implementing a subset, not everything, but a subset that could fit as a per packet network function that can execute on the Tofino 2 platform. At this point, I'm happy to announce that we also were able to acquire Tofino 2 switches for our work. And we were very much driven to perform an analysis that boils down to quantifying the data pre-processing efficiency as a gigabits per second per watt metric, that is an energy efficiency metric through which we can do data pre-processing. Since we didn't really have a realistic workload, it's not contained in the Facebook paper, it's not open source. We just created our own random set of transformations, and we compared essentially what happens if we implement those set of transformations in one of the possibly most optimized way of doing it on an x86 server using fast click and Intel DPDK technology, as compared to doing it in the switch. And so these results on the y-axis portrays that metric, the gigabit per second per watt for data pre-processing. And the key takeaway is that you can see there is a 65x potential improvement on that efficiency metric if we were to perform this transformation on Tofino. So this is certainly a very encouraging result, and we're pursuing work in this direction to try to really create a disaggregated pre-processing service for distributed deep learning that maximizes on the energy efficiency as well. So I'd like to give you some main takeaways for the talk. Deep learning requires a lot of compute, data, and parameters, and distributed deep learning is a must to train large models. This is fairly well established. There are nowadays many forms of parallelism across data and model pipeline, and that are typically combined. Now, network communication often becomes a performance or a scaling bottleneck, and I presented in-network aggregation, faster collective communication, and gradient compression techniques, as well as the fact that we can tackle data ingestion, demand, and bandwidth by using in-network computation. All in all, I have to say that it's been a lot of fun to work at the intersection of machine learning and distributed systems, and it can also be very impactful, as demonstrated, for example, by the fact that our omni-reduced prototype was adopted in production by Meituan. I'd like to acknowledge that this work was only possible also thanks to a whole lot of collaborators. And sorry, Sam, I forgot your name. I was running short on time, but Sam should definitely, be one of the names that sticks up here. And so before I really finish, let me tell you, how does this really continue, right? Are we really just going to continue building systems and, look at the problem from only a system perspective, or perhaps not, right? Because, these days we should really embrace the wild world of deep learning, if we can, of course, stay on top of the research, since it feels very much like a fire hose, all the papers that come out. So I do realize that, I don't really have time to express all the potential for future avenues of work. And if you are really curious, I have lots of thoughts I'm using in a recent keynote that I gave at the distributed ML workshop. But if I have a short version, then I will, pick on Jerome and Eric, who had this beautiful paper in OSDI 2021 of a system called Pollux. And so I would say, how does this story continue? Well, I'd say, in short, it's what Pollux said, which is optimize the training throughput. Right? So a lot of the work that I showed you is about optimizing the system throughput, which is this green curve over here, portrayed in this case as a function of the batch size, but you can generalize, as different properties of the system, right? But in reality, what happens for deep learning is that you also have this other curve, which is typically the statistical efficiency that, as you vary certain parameters, you may gain in throughput, but you may lower in the statistical efficiency. So what you really want to focus on is the training throughput. That is, you want to find the synergy across those two curves and be at the ideal operating point. And I very much believe that this is also true for communication, in that there isn't yet work that analyzes and designs the training process in which the data transfers are elevated as a key parameter of the architecture, where you then can select network communication, right, as you vary here the batch size in order to find the optimal operating point. So that is very much one of the directions that we're taking. And then last but not least, I thought it would be helpful to just tell you, taking a step back about my research profile and the high level pitch of my research. So we certainly consider the space of data centers very much these days, cloud and edge data centers, where what is dominating in those data centers are large scale applications And this entails, of course, deep learning, and probably will be the majority in the near future, but it also entails complex distributed applications that are realized as microservices, key value storage systems, serverless functions. And all of this essentially imposes ever-increasing demand for low latency, high performance, efficiency, and reliability, which are all key requirements that typically one can project in some kind of space in which different trade-off between performance, reliability, and cost exist. And in many cases, it's very hard to come up with a design that strikes an optimum across all these things. And that is because we have to deal with the number one challenge in creative systems, which is the complexity that is entailed, reasoning about very large number of components, users, workloads, and so on. So my research in this context takes a systems approach, which is in nature holistic and reason across all different components and their interactions together. And it seeks to develop techniques and paradigms for systems-aware cross-layer optimizations to better bridge applications and the systems underneath. And I know that's a bit of a mouthful, but really this is the crux of the research that we're doing. And then, to give a concrete example of this, we started about a decade ago when software-defined networking was a major trend, a paradigm shift in computer networking. And we worked on what I like to call the 3Ds of software-defined networking: develop, debug, and deploy, where we introduced programming abstraction, techniques for systematic validation and testing, as well as principal deployment and operational strategies for software-defined networking. That expertise then led us, along with the evolving technological trends, into in-network computing, for which today I presented this central axis of that research agenda in terms of aggregation and offloads. But we've also worked towards what we like to define judicious in-network computing through reusable and composable primitives across a spectrum of applications that also included consensus and telemetry application. We also had a lot of work in terms of predictable performance in cloud computing, where cloud applications need to deal with performance outliers, meet various SLOs and deadlines, and adaptively regulate loads, with the goal of empowering organizations to be able to confidently run their applications in the cloud, and therefore, tackling those challenges and focusing on various building blocks of application, whether those were storage systems, microservices, and serverless applications and data analytics clusters, with successes not just in terms of publication, but also in terms of actually being able to push technology into companies. In this particular case, I highlight the C3 system that was adopted by Elasticsearch and influenced the design of load balancers at Spotify and SoundCloud. And so with that, thank you very much for the attention, and I can take any more questions so we can engage in some more discussions tomorrow. Thank you.
Just quick time check, Philip. I know we might be a little over time, but how much longer can we go for?
Oh, the room is yours as long as you want.
Okay, perfect. So there's no time limit here. Then maybe one question I had, because you brought up some really interesting efficiency plots, right, for the data ETL preprocessing task, right? And then you showed that it was dramatic 65 times more energy efficient than running your Intel CPUs. It almost seems to me like magic. Is it simply because the network hardware is a lot lower power than the Intel CPU, or does it have to do with some bottlenecks like blocking, communication that are being alleviated?
Primarily, it's the former. So it has to do with the fact that that kind of programmable network hardware is really taught for packet processing. And so if you can map those kind of transformations into the hardware, then natively you essentially reap the benefits of very high throughput processing. Whereas if you're concentrating on a general purpose, CPU, then you have to basically deal with the possibility, and that is very much the case, that things are not carried out in that energy efficient way. However, I would say I would caution that that 65x result, while being a true measurement, there is a caveat to it in that we only were able to partially assimilate these transformations. And so, a subset of this, really you could reap the benefits. For another set of transformation, you do need a more general, essentially hardware target to be able to support them. So what we're trying to
might lower the efficiency. The
And then
more
we
general
lower-
you get,
yes.
less efficiency.
Yes.
you're gonna
Yeah,
have.
pretty much, it's that kind of balance.
Right, so that's the trade-off, but I see that the general theme throughout your work is that network hardware can serve as a co-processor, and in general, if you had a choice between a general purpose piece of hardware and a special purpose piece of hardware, the special purpose piece of hardware is always going to be more efficient in terms of speed, in terms of power, in terms of
Yeah, in general, that should be true. That should hold. Otherwise, you will not have, necessarily specialized.
Right. So that leads me to a further question on the deployment and realization of these hardware systems, right? The kind of impression I always get is that hyperscalers are going to be the first to adopt any of these new ways of software programs in hardware, right? And I think the Meituan example you gave, well, I don't know if I would call them a hyperscaler, but it's certainly a big internet company.
It's certainly a big company in
Right,
China.
certainly a big company.
It might not be, the most well-known company in the West. So I often need to qualify what they do, but yes, they're.
Well, at least I knew they would need CTR, right? At least I
Right.
knew that much about Meituan.
Yeah.
So indeed, I asked this question in the context of obviously hyperscalers are the first to jump on these because even a few percent improvement in efficiency is a huge bottom line cost for them to save on. And I've always wondered and struggled with the question at the level of a academic center or a university, how would one start to adopt some of these, right? Maybe it requires something special like setting up a specific cluster or data center that is designed for experimental workloads. Here I'm thinking about my time back at CMU where the Parallel Data Lab had this data center observatory idea. That was a place to put in the kinds of hardware that they would need to demonstrate new concepts, right? And I'm just wondering, like, what is your experience of that, given that you've been able to get this kind of switch hardware into cost?
Sure. So fundamentally, we have subnets that have been allocated to our group, and then we're able to, rather with very low friction, if any, purchase, custom hardware with, a reasonable justification, as to why we need it, and then allocate it, as part of basically that rack space allocation. Obviously, this is not at the size of an hyperscaler, right? Because we're not running, the full data center, but it's typically a sufficient mean to be able to prototype and reach the results at, let's say, a modest scale of a deployment. Beyond that, there are, the usual tools that pertains to computer systems research, whether it is emulation or simulation, in order to, gauge the possibility of how things will operate at scale. And actually, it's interesting, this question, but I would, point out also that in the OmniReduce example, right, the paper itself has a section that describes the experiments that we were able to run at scale. And that was, thanks to having been able to deploy the technology in Meituan, who gave us access to a much larger testbed that, we could use for experimentation. So in a sense, there is a limit, even with our generous resources to, the scale at which we could run these things. But I would say, in a nutshell, really having some rack allocation was very helpful, and being able to acquire the hardware, setting it up, and then being able to demonstrate all these concepts as a real world implementation. And beyond that, we needed the help of industry in order to really gather those more larger results. Yeah.
No, I think that answered my question, and I think the efficiency angle is going to be, and well, if it's not already a topic globally, right, it's going to be an increasingly important buzzword that people will latch on too. So, and I admit, even in my own research, I have not traditionally been thinking about it in terms of efficiency. Well, of course, faster job completion time naturally leads to higher efficiency, right? You spend less watt hours on it, right? But I'm now seeing that there's also the angle that specialized hardware does have lower, power requirements, which is the argument that Google made with their TPUs, right? That they could probably save about 50% or more electricity over an NVIDIA GPU and get about the same amount of performance. So that's all really interesting. Now, okay, I realize I've been the one asking almost all the questions, but does anyone else who's still online or in the room have any questions for our presenter here? Sam, any questions from you since you've known Marco for a while?
No, I think it was a really good talk. And I can ask some of the offline.
All right.
Sounds good. A bit longer discussion.
No friendly fire.
All right, then, without further ado, I think, Philip, let's close on this talk. Once
Thank
more,
you.
round of applause to Marco.